You know what? I'm gonna wing it. Also, hi. We are back after I've been sick for a little bit. Sorry I haven't been streaming. Going to hang out today with Eric and continue working on the shaders. Uh, hey Eric, what's going on?
Hey, so lots of progress since last time, and I'm super excited to work on it again.
Yeah. So you're doing a little bit of time warping here since you showed me something that you'd been working on, or like kind of the end result of the stuff that you've been working on, but you're gonna kind of take us back and show us where we were last time and then kind of work us forward through to where we are now.
Yeah, in a couple hops and skips because I have about 20 commits in between, but
No big deal. It's like, yeah, you did a couple things. It's fine.
just a couple things.
Yeah.
Well, some of them are like, minor code comment change. Like,
And then one
that's
of them made a
commit.
giant laser.
Yeah, that's true. So last time we were at this point where we had some water and we added some heat to it, and weird things happened. So the weirdest thing that would happen is that you add more and more heat around the edges and it just starts making water and you just start making water
I remember this.
everywhere,
Yeah.
all of it. Yeah, so
And
that's obviously not what's supposed to happen.
I mean, how do you know, right? You could just want to
Uh,
create a lot of water.
that's true. I'm pretty sure it breaks all physics.
Well, like conservation of mass or what conservation of
Yeah,
energy.
that's a good one.
It's fine.
So anyway, here's the problem.
Hmm.
Um, so this is the state shader that takes an input texture and the heat texture and modifies some other texture based upon that
Right.
for a transition hot and a transition cold. So if it transitions to hot, you do some stuff.
Hmm.
If the heat pixel is greater than transition hot, and if the heat pixel is less than transition cold, it transitions in the other direction. So what's wrong with this? Is that
So
this pixel
plus,
dot A
yeah.
is set to zero point 0.5 plus zero point 0.5 times whatever. And if neither of these happen, it's zero, which means it's negative maximum every time.
Oh, huh.
Yeah,
Well, that'll do it.
right? So I updated it to this, where otherwise it's
Ah,
zero.
gotcha. Right. Okay. Yeah, because zero is negative maximum, zero is not zero.
Yeah, and
It's,
then that made things break slightly less. So if we go into heat view, you can see I'm adding heat, and
hmm.
then eventually,
Hey, and you're not adding more water now.
no, but I'm also not adding any steam, which
Oh,
is kind of
right.
dwarf.
Hmm. So what happened there?
Uh, well, it eventually works.
Okay.
So
So
you
it's
hope
like,
and pray. Hey, we got
oh,
some
hey,
steam. We got
all
some
right,
steam. There it goes. Woo! It's
neat.
happening. It's happening. Anyway, so this isn't really what we want to happen, but it kind of, at least it doesn't create more water. And
Yeah.
if I take the heat away from up here, nothing happens because it's not implemented in that direction.
Oh,
All right.
okay, yeah. It was only one.
Yeah. So then I realized that capacities were killing me. So capacities are the things that we went into in the heat 2 shader.
Right.
We want to be as realistic as possible, so everything has a different conductivity, so it transmits heat more or less well, and everything has a different capacity.
Hmm.
So water can hold more heat than copper.
Right.
Uh, Basically, I just took all of that out. Whoop,
Okay.
it's all gone. And temperature is just heat over height.
So everything has the same heat capacity.
Yes, which makes things work a lot better,
Okay.
or at least more easily right now.
Yeah.
It's something that we will need to, spoiler alert, will need to implement later. But here you can see then, yay, heat does something
Huh.
and you get your steam. Everybody's happy.
Yeah. Nice. All
Um,
right.
yeah, so that's the basics of like things actually work. Uh, this kind of works.
Lava
I'm not
on.
sure. Oh, okay, these don't spawn with heat. Crap. Well, in any case, they would do something like that, and it would make some steam, and then here the steam is turning back into water, and woohoo!
Whoa, neat.
Yeah,
Okay, yeah, that's
and
awesome.
then we just jump ahead in time like a bunch.
Yeah,
I'm actually gonna have to restart Unity for it because
just go all the way forward.
it changes too much. No, Unity. There we
Bye.
go. Kill it. Kill it. Ah, there we go. Flow.
Yeah, I think if you do
Yeah.
save project, it'll fix that.
Yeah.
Maybe. I think
Okay.
so.
File save project.
Unity
Eh.
saves are weird, but if it doesn't, that would be
Yeah.
strange.
So I had a bunch of stuff in the meantime. I reorganized all the code to be
Hmm.
more clear. So if people are also following through the flow repository, maybe they can actually make sense of it now without my explanations.
Oh yeah, I should link
Uh,
that. That would probably be a smart thing to do.
Probably.
Okay, yeah. So for
Um,
now on, I'll link that in the video descriptions and stuff so that y'all can get the code.
all right, that sounds cool. And then after that, I implemented Obsidian, which is a state of lava. So if you have lava and then you cool it down a bunch, you get Obsidian. Um, and Obsidian is neat because it can turn back into lava if you heat it up.
That is really
Uh,
cool.
yeah. But then I wanted to add a secondary state change, which is dirt. So if you have dirt and then you heat that up a bunch, it turns into lava. But again, if you cool it down, it turns back into obsidian instead of turning into dirt. And we can go into how that exactly
Huh.
works a little bit later.
Is that what it's doing
But
kind of down there at the bottom right now? Is it's turning the dirt into lava? It's
yes,
like
so
melting
there's
through
enough
it.
heat.
Oh, that's a lot of heat. Yeah.
Yeah, there's a
Wait,
lot of heat in there.
why
You
is it
can
not
see
melting through
the
the sidewalls?
it is, but more slowly.
Oh, okay. Got it.
Um, yeah, it's only 0.84 heat on the left hand side where it's or temperature, and the middle temperature is like 1.3.
Got it. Okay.
Yeah,
Yeah, so it's just melting right through that.
num num num, pretty much. And yeah, so after that, I worked a bit more on the elements themselves. So now we,
Hmm.
we can place, you might have seen it before, but you can place with the left click kind of a circle of element.
I just realized I didn't switch away from face cam.
You didn't switch from face cam. Oh no!
Rip. Oh my gosh. So yeah, well that sucks.
Well,
Well, you heard the good description of it.
yeah.
But okay, so hold on. Can you at least show this part with the lava and everything again?
Yes, I can.
Whoops.
Uh,
Hashtag production value.
yes, that's the production value. Yeah, you can tell I'm watching the stream, right?
Oh yeah, yeah, yeah.
I totally
Thanks
didn't
for
see that.
I'm gonna put this at least a little bit on you.
Yeah, that's yeah.
No, it's
Now
my
I
bad.
am. Uh,
Okay, hold
right.
on.
So, oh, and I just noticed
Whoops.
that actually that's below screen if I maximize it.
You know what? We
What you
just
done?
nailed this.
Yeah. So, hello and welcome
Oh,
to.
okay, take two. We're just going around again. One more time.
Yeah. Um,
Oh my
yeah.
gosh.
Visual Studio Code not so interesting, but this part super
Yeah.
interesting.
All right, this part's
So,
really cool. So we're gonna do this part.
yeah,
Hey, well, at
we
least we
got
didn't
some
get to the
lava.
part where you're doing the water cycle, because spoiler
That's
alert,
true.
that's awesome. So
But yeah,
we're gonna be on screen for that one.
medium spoilers. There's a water cycle.
Yeah,
Um,
medium spoilers.
yeah. So there's lava, and it's super. Everybody loves it.
Hmm.
We have the obsidian, which we can heat up. It becomes lava. Same thing with dirt. You add some heat, and it becomes lava. Everybody's happy. Cool it down, it goes back to obsidian. Hooray!
Yay.
You can see it actually turning into obsidian here on the right hand side,
Yeah, is
just
this like
because
melting through?
the dirt is taking enough heat away. But I think this lava is going to come back over and melt the obsidian again. Maybe the values need tuning. I don't know.
Yeah. Hey, look, it's eating through on that side over there.
It did.
Nice.
Um, yeah, so new paintbrushes, left click, middle click, and right click is remove.
And it removes only that element, right? So you
Yeah,
can.
so I could just do dirt down here.
That's so
Um,
cool.
yeah, and then you add some water to it, and it turns into steam. Hooray!
Whoosh. Now you just need a
And
sweet
if you
sound effect for
notice,
that.
Yeah, there's little. If you go into heat view, there's these little clouds here. It's actually raining a little bit here at the top as it's cooling.
Oh, that's awesome. Wait, and then is there heat in the air that's like causing it to go back
It's
up?
just it's just going to such a small amount that the heat on it makes it above the temperature gradient. It goes back up.
Ha.
Eventually, it will reach down here
Oh,
and
as it
stop. So this is basically what hail does, right? Like hail does the same
yeah.
thing in real life.
Oh, that's so weird, but yeah, that's exactly how that works. Huh.
Well, I'm not sure. Maybe some whatever weather
No,
scientist
that's
can correct me on that, but
no,
pretty
no,
sure that's
that's
how it works.
yeah, yeah, because if it's the like hail occurs when there's freezing rain over hot land.
Hmm. Hmm.
And yeah, then it, like the convection of the air blows it back up into the clouds, and then you get like this, it refreezes, and that's how it grows in size.
Huh.
So
Well, so we're gonna pretend this is convection
there you go.
instead of
That's
just reaching
it's
a temperature limit.
convection with air quotes.
Yes, very good. It's funny because it's air. Well, uh, in any case, yeah, so we have steam, we have
Nerd
water, and
jokes.
obviously, if we can go between steam and water, and the water can go down to the lava and make more steam, then we can do the water cycle, which has been my since day one
Yep.
objective with this simulator game thing, whatever it is. Uh, so if we take
This
some
is so
dirt and
cool.
make a nice ramp and some copper
Pretty cool
and
ramp you
make
got
a
there.
yeah, nice make a I don't know what this is, a heat sink up here.
Yep.
I'm actually going to take all the heat out of this heat sink just to
Wait, it spawns with heat?
make sure it's nice and cold. Hmm? Yeah, everything spawns with heat now.
Oh, I see. So it just spawns like with a medium amount of heat.
Yeah, it spawns at point 0.3.
Okay, got it.
Point 0.3 heats.
So what you doing down
This.
here?
Yeah, so this is a ramp because I'm gonna be cooling some water. Actually, that's way too low ramp. Ramp needs to be way up here. So this is just gonna catch the water and funnel it back down into the lava, which is down here.
All right.
Obviously, MS Paint skills, years of practice come in handy right here.
We can work on brushes at some point.
Yes. So here's some lava, everybody's favorite.
Look at it being lava.
Yeah, and then we just add a little bit of water up here, and we watch what happens. Ta-da! Round of circles.
Yeah.
Nice.
It's so cool.
Yeah, so if we go into Steam view, you can see the steam being created there and going up. And if you go into water, you can see it falling down and going back down. So this forms the basis of like what I kind of want to do with this game is to make elements change, make circles of things that happen, and like put a steam generator here or something.
Hmm. Like a little
So you
turbine.
can yeah, you can funnel this in a nice little funnel or whatever. And here you have high pressure steam turning your turbine.
That's so cool.
Yeah. Problem with this though is they're making obsidian here at the barrier.
It's
So
making obsidian. Oh, right,
yeah, because
because the
the
water's
lava's
cooling it
cooling.
down. Yeah.
Yeah.
Uh-oh,
So eventually this will stop.
yeah, your lava's
And
running out.
yeah, so I can actually just take away the obsidian,
And then it does this.
uh, which does a lot, it makes a lot more steam because you have a lot more contact surface.
Yeah. Interesting. So
Yeah.
what if you used a like a copper heat barrier or copper barrier between the water and the lava? Copper
Like
doesn't melt, does it, right now?
copper actually, yeah, it does not melt at the moment. We can just take all the obsidian away. Um, let's find out. Oh no, the water's still going over it. So
Dang it, water.
bigger copper heat barrier.
Yep.
Take away the water from this side. Take away the. Well, I'm just gonna add some heat to that obsidian because like that's
Yeah.
ridiculous now.
I'll just melt it.
Yeah. There you go. You got steam right at the barrier.
That is so freaking cool.
Yeah. So the heat's coming through the copper and
Yeah. And
right up.
now you got your little heat or water cycle going.
Yeah, and you're not really turning obsidian because the heat flows here faster than it does away from
You know what we just did?
the
We just played the
copper.
game.
We just played the game. Yeah,
Yeah.
so this is like part of the game.
Yeah. You're like, oh yeah, we have this problem with our water or with our steam generator. It keeps turning the lava into obsidian. I have a
Yeah,
solution.
this is this is the solution. Yeah, so from time to time, random elements can spawn and stuff and mess up your things. And I implemented that, and it looks like this. Oh no.
Elements everywhere.
Yeah, and if that happens too many times, then things just start to go crazy.
Yeah,
But that's
that's a little
okay.
crazy. It's like a I don't know, some piece of modern art just like
Yeah,
throwing yeah. You just threw a bunch of paint at the screen. Except in this
yeah,
case
and
the
then you get
paint
to
is all
watch and see what
reacting.
happens. Yes,
So
exactly.
what does this settle into? Like have you just run this for, 20 minutes and seen what it does?
I have not, but I can turn up the speed to 10 times speed. Oh, now my computer's crying.
Yeah, I was
Go to
gonna say this is
stats.
probably
4. The FPS is 4.
yeah, this is just maximum amount of updates per frame, right?
Yeah. So it's doing 6,000 updates per frame.
That's a lot. Your GPU is just going to be sad.
It's on beast mode right now.
Yeah.
I wonder what it's actually using. See, performance. Oh, I can't drag my task manager. Oh, there we go. 54% and 100% GPU. Yep.
Okay, so well, you're definitely GPU bound.
Yep. But that's good because
Yeah,
that's what I want it to be.
yeah, exactly. Like you just want to
Uh,
use that as much as you can. Hey, that
it
lava
looks
is just
like,
bye
yeah,
lava.
yeah. So we got no more lava. So let's turn this down a bit again. That's normalish speed. Yeah, so the heat just kind of evens out. Everything looks to be like 0.3
Yeah.
ish. And then because there's no barrier anymore, this water is just going to keep falling forever, which is also cool. I mean, I'm
Oh,
not
it's
sure if
gonna
I want
fall
that to
right
be,
from the top of the screen.
yeah, so I'm not sure that I want that to be a mechanic people can exploit because like you make a little bit of steam and you let it go up, and
Oh,
all of a sudden
right.
it's at the bottom, so it can go up again, and
Yeah.
you just have like an infinite steam pipe.
Well, you could turn off wrapping on the y-axis, right? And then that would
I
just
could,
stop that.
I could. Um, that is other issues.
Oh, does it?
Yeah, because if I click here at the edge, you can see it makes it the top as well.
Yeah.
Or if I actually go like below the screen. So yeah, we gotta solve that as well.
Well,
Otherwise,
so I
it'll
mean
be
that's what
like,
I'm
oh
saying. Like
no, out of bounds.
if you turn off wrapping, then it wouldn't
Yeah.
do that.
Well, I mean, with my screen to world point,
Oh, there's actually your code that does
pixel.
that?
Well, it's the pixel. So you can see the top left here, like negative 57,
Right.
157.
Yeah.
But if I click there, it still makes a thing
Yeah.
because it's able to wrap. Whereas if I didn't wrap and I click there, the game would crash. So I'd have to build
All
in
right.
handling for that.
Yeah, that's true.
And right now, I'm
Uh,
too lazy.
you can do another cool I don't know, another cool trick since you are
Hmm.
wrapping.
Yeah.
You could make it. Hold on, where's a whiteboard here? I don't really need the whiteboard. I just like drawing.
Uh, let's see. Is whiteboard on? Oh
Nope.
yeah, that's me. Uh,
Uh-oh.
whiteboard on. Production value.
All right. So you could take this texture and
Yeah.
put a copy here and then put another copy over here and
To
then
tile it.
yeah, so you can tile it and or you could even stretch this quad and have the UV coordinate stretch.
Hmm.
You just need a custom shader, I think, for that. Anyway, you can clear my little things, but yeah, the easiest thing to do would just be to duplicate this quad and set it up next to itself,
Yeah.
and then yeah, just use the same world rendered material.
Hmm. Can also do this.
Yes,
Just
which
zoom
makes
in.
this, and you can zoom in.
Hooray.
How well does it render with something
Water.
this big?
What do you mean? How does it render?
Let's no no how like how what's the
Like,
performance like? Wow.
still max. Let's
Well,
put some lava all
yeah.
over it. I don't know. Now we got reactions.
Holy cow.
Still
Yeah, and that looks
max.
so good with it being that big.
Copper.
Is
And
that?
you can see the update rate of the update call
Yep.
because
Yeah. That's the rate of the call exactly. So you need to do a
so that drops
Brescianim's.
it.
So the Brescianim's line drawing algorithm, you need to throw that in there so that way you're always drawing lines between your points.
Okay. I should also probably just do that method better.
What do you mean? Oh, yeah,
Um,
that's probably true. At some point, we should probably fix that.
yeah, because whenever I click that, you see the FPS drops to like 20 or 30
Yeah. Well,
because
because
it's
it's constantly reading back the texture from the GPU, right? And then doing a full
yeah
texture update.
like every texture, it's not optimized.
It's fine.
Yay!
Look at all that heat.
Uh,
So
it's pretty
now
cool.
that you've caught me up completely,
Mhm.
what you want to do today? What do you want to work on?
So I got a couple things. One is the water to multiples of steam. So because one, like you boil a pot of water and you get a room full of steam.
Hmm.
Um, and the other is superheating and supercooling, which is like if the water, if there's more than zero point 0.9 water in a cell, it will
Hmm.
not turn to steam because there's quote unquote too much pressure. So then you can like flash boil an entire section of water by putting it into
Right.
a closed container, heating it up really hot, and then opening one edge.
Do you have a concept of pressure right now?
Uh,
You
the pressure is pretty much just the amount,
so oh, okay. Well, that works. So
kind of,
what I'm
right?
wondering is if you have a column and you remove the thing at the like do the three holes test that you were talking about,
Yes, the three holes test.
like what happens?
Yeah, for those not familiar with the three holes test, if you make a hole in this water column here, here, and here, the pressure at the bottom should shoot the water out like that, exaggerated. This one should shoot less far, and this one should kind of dribble down. Probably not going to do that,
If your universe has pressure.
but let's find out. Actually, got it. Oh, that's whiteboarding stuff.
I would like this slider to go this direction.
This, you pull this slider in that direction. Uh, all right, so no, that's add, that's remove. There we go. So water's dribbling,
Yep, I see a dribble.
dribbly, dribbly. Uh, oh, that's now I'm still in water. I'm so good at this. We can move the water down here. And now I want to remove dirt here. Hmm, block that up again.
Is it kind of working?
I mean, maybe.
See, I don't have a theory as to why it would work, so that's the only problem.
Uh, let's see.
Other
What
than
happens?
it's building a pile on top of itself there, and that's why it's going to be going further. So like if you do this one down here, because there's ground down there,
Yeah,
like that's why it's going further.
this might be a false positive,
I
and
think
I
it's a
should
false
take away the
positive.
ground.
Yeah. Also, do two water columns balance out? Is that a thing?
I never tested that. That's
All
something
right.
I want to test
That's
with
probably an
most
easy
people.
one. Let's test that one first.
Yep. So we have a thin column of water
For those of you
and
following along at
a
home,
thick. If you have two columns of water, uh, which eventually balance, or I mean, eventually settle. Let's just make this one really low.
by water.
Yeah. So this is what I mean by the concept of pressure. You see, it keeps going down here because it's trying to
Yeah.
maintain some gradient along the height. So yeah, like this will flow into there um, because it wants to maintain that gradient, and so this will
Huh.
come up.
So there is kind of pressure then, because otherwise it
Yeah,
wouldn't do that.
yeah. There's sort of pressure. So if I go 5,000 speed,
And it'll eventually get there.
yeah,
Okay.
it'll
Well, this is promising, right? Because it eventually evens out, which means that so it's trying to maintain a gradient according to because of how you implemented gravity, right?
yeah. So gravity isn't exactly gravity. It's just that water wants to be lower than its southern neighbor.
Hmm.
And so when you have flow, the flow of this cell in regards to this one, it adds a little bit to the height here. It subtracts a little bit from the height here when determining can it flow. So what ends up is if you have 0.5 here and 0.5 here, this one will say, oh, I'm actually 0.51 and this is
Hmm.
0.49. And so it will flow up. And the actual result will be 0.49 here and 0.51 here, giving it a quote unquote gravity.
Interesting. And so that and that works through that little pipe connector in the bottom because what
That's from natural height flow. So
right.
it'll flow in that direction.
Yeah, because if one is because it will be essentially there will be less in the one beside it because its gradient will be lower.
Yeah,
Yeah, so until you even out, then you don't have the same gradient, which means it'll flow from the one with the higher with like the bigger gradient to the one with the lower gradient.
yeah. So if you
Okay, so it's
visualize
not
that two
really
colors.
pressure, but it's kind of the
Yeah.
effect of it. Yeah, there you go. Nice visual.
So these angles are the same, and this distance is what it's determining
Oh,
as
you're
height.
breaking out the math.
Yeah, so that that will flow into there until these triangles are the same size,
Yeah.
and then it's equal. Hooray!
Hooray. Well, good. So, but okay, so out of these things, so superheating and supercooling rely on pressure, right? Because you want to make basically you want to make a pressure vessel.
Yes.
So, because I would imagine you would want to be able to do something like you can superheat steam, or not even superheat steam. You can just heat up a ton of steam in an area, and then make it compress the fluid underneath it, open up a little valve, and then have the water shoot out because the steam is super high pressure.
Uh, I mean, that kind of works already. If you have, um, we can have like a small amount of pressure vessel here, and we add some water. But here you have to actually boil this water um, and have the steam created.
Hmm.
So here they'll all balance out because one water makes one steam.
Oh, right. So now, so that's the we can that's probably an easier thing to tackle today, right? Like getting
Maybe,
water to turn into multiple steam. Wait, no, I say maybe.
maybe. I have my doubts about that. But yeah, so if you build a pressure vessel by like stacking obsidian and dirt and copper to make really high walls,
Yeah.
and then you can have like over one in this layer. Here I'm just going to add a whole bunch of steam and add a whole bunch of water. So here you can see it already starting to flow over the sides, which is kind of like outwards,
Oh, it's just
and
like going
it's flowing
straight through
outwards.
it.
Yeah, because this is taller than that, so it's like it's over
Oh,
pressurized and breaking your pressure vessel. So that kind of works.
all right. Yeah.
Uh, but what I'm looking for is like I have a pressure vessel here,
Hmm.
and I fill it with water. So this is water. I mean, it's already starting to push a little bit, quote unquote, push on the sides.
Yeah, you can see it escaping a little.
Where, yeah, where it's low. I gotta really build these walls up to full capacity if I want the water to stay in there. But now when I add a little bit of heat, you get steam immediately, right? But if this was under pressure, the water could not turn to steam
Right.
because there wouldn't be anywhere for it to go. So now it's just all steam,
Hmm.
which is fine. But I want it to stay as all of this to stay as water
Hmm.
while it has a massive amount of heat in it. And then when you go like this, it just
It
all
just
turns to steam at once.
yeah, turns to steam and just like shoots out of the end of it.
Yeah, which you can go totally look up YouTube videos of explosive decompression, and it's awesome.
So yeah, it's pretty ridiculous. It's like what is that called? Catastrophic failure?
Yeah, that's a
Yeah,
good one for it.
it's catastrophic failure.
Yeah.
So,
Right. So the reason that I
hmm,
was saying that maybe turning one water to 10 steam is not the easiest is because to maintain your temperature during that changeover,
hmm.
you have to decrease the heat capacity of
Oh no.
steam by 10 times that of
Uh-oh.
water. Yeah, so that you maintain the same number of heat,
Uh-oh.
yeah, with the same temperature. So
So what you're
lives that
saying is,
capacity back
right,
in.
this thing that we were working on before might have to come back.
Yeah,
Well,
yeah.
okay, so what we could do is introduce heat capacity and have heat capacity be one everywhere and like get all the pieces in so that
Uh-huh.
it's what am I saying? So that all the code is in and we show that, when everything is one, nothing changes. And then you change the heat capacity of one element and then just see what screws up, and we kind of go from there in the debugging process.
Hmm. Yes. We will both have to change the heat capacity and the transition stage at the same time.
In the transition stage, what is? Oh,
So
like
if
for the right. Okay. So you mean the transition amount, like 1 to 10?
yeah, yeah. So if steam has only a tenth of the heat capacity, then
Right.
when one steam heats up, it needs to take that much heat and distribute it over 10 units.
So just thinking about this, the change we would need to make is to the state change shader, just in general. Like there would have to be a transition to and transition from capacities, like on a per unit
Uh,
basis.
yes, it would have to be implemented in there. It also has to be implemented in the heat flow shader
Wait, why does it matter in the heat flow shader?
because that you have to calculate temperature. Actually, in the temperature shader, um, because in here you have to calculate the temperature flow, which relies on this pixel divided by height, but it's not height; it's per capacity as well, the average capacity that we have to add
Height
back in,
height times capacity
times average capacity. Yeah.
times average capacity. Okay, this might be where we got screwed up last time.
Yes, it probably is.
No, I mean, well, because I didn't go back and do the math on this for of whether average capacity actually gives you the same value or not.
Hmm.
Like so because there's two ways of doing it, right? Like you can have the total heat, you can use the total heat and the average capacity, or
Hmm.
and some function of the individual capacities, uh, or you can do the individual heat and individual capacity and then do a function of those things. You see what I'm saying?
Yeah. So I'm going to try to write it out here.
Yeah.
So that's my thinking.
So, uh, can you write? I mean, I know that
Mm,
this is correct, but instead of average capacity, you can do f of capacities here, like just
F
function
cap.
of yeah of cap one comma cap two comma dot dot dot. Yeah. Okay. Cool. So you see what I'm saying? Like there's some function which is probably the average, but then the other way of doing this is temperature equals f of heat over amount times cap one, or amount one times cap one, I guess,
Yeah.
and then
So
comma,
amount total.
or there's heat one, I guess heat one over amount one times cap one. Like, because then you have a
Yeah.
per element heat and you have a per element amounts and capacity, and then so it's that comma that, right?
Yeah. That again,
Yeah, all of this again
which
for
is
two.
which is just heating. Well, which is if you replace the comma with a plus sign, right? No, and then you have to divide them all.
So okay, so if you write it like this, and
Hmm.
then the thing that we have to show is that if we can use the averages, if we can say that these two things are equal. Wow, my box is just the worst box that you've
Good
ever,
work on your MS
you know,
Paint, man.
you know what? Yeah, I know. So, but if we could show, I'm gonna do little arrows. If these two things are equal, like if we can mathematically show that these are equal, then we can use the average and
Sweet
we'll be safe.
arrows, man. Sweet
Yeah.
arrows.
Okay. See, I worked on my MS Paint skills there in like the 5 seconds
Yeah.
between those.
It's a quick practice session.
Yeah, exactly. Um,
Uh,
okay, so but
so
does that sound right to you? That if we can show that these two things are equal, then we can use then f can be the average.
I mean, it makes sense to me.
All right, going in on the
Uh,
math.
so that I think is true. Like first we have to figure out how it works.
Uh, what do you mean
Uh,
how it works?
so we
Thanks, Lucky
know
Fox.
we know that this is true, right? If there's only one element, the temperature is a heat divided by the amount times the capacity.
That's true.
Okay. So then,
So far, so good. We're
so,
basic physics.
yeah, that's all right. Well, like, is capacity on the bottom? Is capacity on the top?
I guess
So
well,
that's what we're working with.
yeah, got it.
Because if you have the same amount of heat and the same amount of material,
Yeah,
a item with a lower heat capacity will have a higher temperature.
I like how you went for the inverse logic there and got it.
All right, cool.
Well, I mean, dividing by something that went down is, I don't know. To me, that's more confusing than dividing by something that goes up.
Well, you would
It
have to
was
multiply by something that goes up.
well, like so heat capacity. Anyway, I just like the way that you thought about that because to me, I would have thought, okay, well, if heat capacity goes up, then that means the temperature should go down,
Heat capacity, if that
right?
goes
So
up, that
same heat, same amount. Capacity goes
yeah.
up.
Something with a
Something with a
higher
higher capacity,
capacity will
right? Because
have
capacity
a
doesn't change.
lower
Okay,
temperature.
yeah, it should have a lower temperature because it's
Yeah.
storing more heat at
Yes.
yeah per degree.
More heat per
Yep.
per
All right, we
temperature.
have beaten the crap out of this one. So I think we're
Cool.
hold on. Big ol'
Next.
check mark. Yep.
Clear and true.
Yep. All
So
right.
if you have a box with two elements in it, so we're going back to high school chemistry now,
Yeah.
and if you mix salt water at 300
Oh my God.
Kelvin
No.
with
Okay. No. You know what we're gonna do? You know what we're gonna do? We're gonna do this in an easier way because it should be true that if this formula, if our formula is gonna hold, it should be true that if you have the same element twice, then that should be the same thing as having twice as much of that element. Does that does what I said just make sense? Did I say that the right way?
assuming that you split the heat between the two.
Yeah, you split the heat between the two, and then you
Yeah.
say I have the same element twice. It should be exactly the same as having twice as much of that element.
Yeah.
Which
So one times one, one over one times one is one, and that's one. Divided by two is one. And if you have one divided by one, one times one, everything is one, and everybody's happy.
okay, what if we do this with something that's not one?
But I love using one because everything always works.
yeah, okay. And I love using no
So,
op because I always know what it does.
yes. Assembler code. So here we have like,
yeah,
I don't know,
nerd
10 heat
joke, assembly joke.
divided by, yeah, 10 amount and the
Yep.
capacity, which
Oh
will make
no,
that
you
times
don't get to.
3.
No, no, no.
5 amount
Sure.
times 3 cap.
Yeah, there you
Oh
go.
man, we're gonna
Oh,
get
let's get some
fun
fractions
stuff.
up in here.
So this is like 2/3. The temperature is equal to 2/3.
hmm
I guess it should be the other way around, huh? 0.6 equals.
Yep, nailed it.
All right. So here we take that same. We hope it's 0.6,
hmm
but whatever it is, it equals
So there should be 5 heat in
half the
each
heat.
one, right?
Yeah. And we're just dividing
And
everything
half the
by
amount.
half. So that's 2.5 times the
Yeah,
same capacity
right.
plus that again. And all of that divided by 2. So what's this? 2.5
So
times 3 is 7.5. Let me get up my calculator.
yeah, just punch that into the old calculator.
But
Like we could do this
2
analytically, but
2.5
you
times
know we're
3.
not gonna
Ah,
do.
yes. 5 divided by 7.5 is that much.
It's
Ooh,
two
that's looking
thirds.
good.
Yep.
Times 2 divided by 2
All right. I'm
is 2
sufficiently
thirds.
convinced. Since you
Very
used
good.
numbers that weren't one, then we're gonna. You know what? But we're only putting 2 check marks on this one.
All right, all right. So what happens if they have different amounts?
Yeah.
So this one is we have 10 heat over 2.5 of a 6 capacity, which is also conveniently 2/3 because you have twice as much heat and you have twice as much capacity, which
hmm
means it's the same amount. And then the math is all the same and it's 0.6 again.
Hold on. Wait. How is this one also 0.6?
Because I multiplied the top and bottom by 2 in this equation, that changes nothing.
Oh, right. Okay. Yeah. Got it. Temperature stayed the same. Okay. Sweet.
So,
So it works at
it,
least for the identity case. So
yeah,
that's good.
but is this true for this case?
Right. That's what we
So
need to
here
do.
we have a total of 15 heat, and we have a total of 5 amount
hmm
times the average capacity, which is 6 plus 3 divided by 2. And get out EO calculator. That's 9 divided by 2 times 5. And then 15 divided by 22.5 is the same number. Ba, ba, ba.
Cool. All right. Yeah, I'm pretty convinced. But you know what? This one gets one check mark.
God,
Because you know what,
clever.
we verified it with one data point, so my confidence has been decreasing over time, but that's that's okay. I still think that this is right. I'm
Yeah. I
yeah,
mean, so
that's not the eraser.
what heat heat here is just heat one plus heat two,
Hmm.
and amount here is just amount one plus amount two. And what did we do with the capacities? We had cap one plus cap two divided by two.
Yeah,
Can we rearrange that equation to give us this one at the bottom?
right.
The answer is probably.
Well, let's do it.
All right, here you go. Um, let's just multiply this by two.
Yep.
Make that go mostly away. Oh man, it's gonna be messy.
So
Be a little
just
bit messy.
to
We
fill
can.
people in on the reason I'm suspicious of this, because it's obviously worked so far when we've gone through this, but the reason I'm suspicious is because this really looks like the resistors in parallel equation, and
Mm,
you can't simplify the resistors in parallel equation. Like you have
that's
to do
true.
it as it is because it's that equation is it's 1 over a plus 1 over b. It's the sum of the reciprocals, or it's the reciprocal of the sum of reciprocals. So if you have three resistors in parallel, this is the ending. This ends up being the resistance, and this thing looks a lot like that. So
for, for
yeah,
for those of you that like normal stuff, this is
I'm
the
not going to erase this.
resistors in parallel.
Yeah, if you do it with units and whatever, then normal stuff. Yeah, thanks.
Normal stuff. And for series, it's just adding for those that also
Yeah,
want to know that. In any case,
no,
so we have some stuff. We're dividing it here, and I don't want
yeah.
to do long math. This looks like it's going to be long math.
How's this gonna be
So
long
I'm
math?
I'm saying it's good. That's what I'm saying. I can just take this
You
two
saying it's
out
good?
with that divided by,
All
and
right.
stick it to the other side.
Wait, no, you can't.
No,
Wait,
can't I?
hold on. That is. Oh wait, hold on. It's
The
divided
whole
by
thing is
two.
divided by all
It's
of
divided
that
by
on the
two
bottom.
times. So this done. It just cancels out this two here.
Yeah, it does.
Okay.
But
Well,
first I
that's
had to
good.
move it over there to make sure that
Okay.
everything is kosher.
I see. Okay.
Yeah.
So you did that. Uh,
Hooray.
so now,
uh, so this this isn't distributed. This isn't or distributable. Like I can't just take heat one plus heat two out of this because they're
right.
different
So you got
amounts
to
of
multiply heat
capacities.
one by the denominator down here, and then heat two
Yeah,
by the denominator up down there.
that's troublesome. I'm not sure I want to do that yet. Uh, can I take anything else out of here that
I
makes
mean,
sense?
no, and you. Oh, this is gonna be a big pain in the butt.
Right? That's what I was saying.
Yeah, because this is gonna end up. I mean, this is the what is that called? Like the two-term expansion thing. Remember, there's a name for that.
Uh, PEMDAS? No, that's order operations.
No, it's like
Foil. First outside,
foil.
inside last.
Yep. Yeah, it's foiling. We gotta foil. You gotta foil this out if you wanted to, like, because then you could multiply both sides by these,
All right, we're gonna save this step. We're gonna do it here.
or we could just pretend that this is gonna work and then go write a whole bunch of code that relies on it working, and then
Uh,
kind of complain when it
let's see if
doesn't
it works.
work.
First, wait, that's the
No,
first, and then
actually,
the
okay. So I don't think you had
outside.
to. I don't think you had to foil this yet. I think we will
No?
at some point, but I don't think you have to do it right now.
Okay, because we're
So,
gonna write the code first.
well, because you can, I think we can balance these. So we can get this sum
Inverse.
first, like make this into like have a common denominator.
Okay, so we take this and we put it here, and we take this and we put it here, and we take those. Oh God, this is so great. And we put it here,
What in the?
like that.
Yeah, right. Yes.
Wait, yeah, that
So,
works right.
yep.
And then we can remove brace because I'm over bracing. Am I though? No. There we go. Up, 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 up. Hey, look, there's cap two times heat one, heat two times cap one. All right, and then we have a common denominator.
Wait. Okay. Yeah. So we're getting
That's
into
all
weird.
over.
Okay, we're getting in a weird spot here.
Yeah,
Well, because the denominators aren't the same, right? Because this
we're
is
digging too deep.
the sum of the amounts.
But we can multiply all of this up there and all of this up there, and then multiply, keep their bottoms
Yeah,
by the whole thing, and
right.
then
So yeah,
we're out of
that just
denominator territory, and people are happy.
yeah,
Yeah, gotta copy all of that. Oh, and now
math
you
is
foil
fun.
all that out. Math
Okay,
is
yeah.
fun.
Now you got to foil just all of it. So
So this one's easy because it's just a multiplier,
right, yeah, it's heat
but I
one.
might not
Well,
want
this
to
one,
touch that.
yeah, this one, that one, I don't think you need to. If the other side is going to resolve, it's going to be obvious, right?
Yeah. All right, so we keep that step, and we copy paste it down here. Uh, all right, so there's that times that, or that plus that times that plus that time. No, these ones have to go first, I think.
So we can already you can look at this and know that it's not going to resolve.
Can you?
Yes, because there's no subtractions.
Uh-oh.
And so because there's no subtractions, there's no chance that foiling this will cause something to cancel out. And there's an amount being summed here, and there's no amount being summed over here.
Did I screw up the math?
No, I think that this is actually just the resistors and parallel equation, and you actually can't use the average.
God
I know. I
damn.
think that I think this might have been the reason that this didn't work.
All right, so we know
So,
this is true.
all right, hold on. Wind it back all the way back to the beginning. Yeah.
Yeah. So if we have two of them, uh, we can't just do this. We have to do. Uh,
Is that the problem? Is that okay? So now I wish I could go back and see what our original equation was. But is the
I
temperature
mean,
not the
I have
sum of
Control
the
Z.
two? Oh yeah, there we go.
There we go. Control Z
So
it all the way.
F. So right. So this is the temperature. This is what we hope is true.
That's what you hope is true. Yeah.
Yeah. And this is so. But hold on. Okay. But maybe is this not true? That the temperature is the sum of the heats? Maybe this is the part of the equation that isn't true.
Let me check my high school physics real quick.
Get on the old
Mixing
Google.
two liquids.
Hmm.
Equation.
Yeah. Hold on. Is it total heat of two?
Ta-da!
Yeah. Hold on. So this formula equals. Oh, it's the. Hold on. M1 C1 is M1 mass, C1 is capacity or heat capacity.
Two liquids for each heat capacity. Yeah. So that's our equation. Thanks, Google.
Nailed it. Okay, so
Yeah.
this is actually different than what we had because this has the capacities on top as well, right?
Yep.
Because it's mass times capacity. So there's mass times capacity times
Times temperature.
temperature times original
But
temperature. So it's the
mass times capacity times temperature
oh, it's a
is
weighted
heat,
average.
right?
It's a weighted average.
Yeah, but this is mass times capacity times temperature. That's just heat.
Mass times capacity. Okay, right.
So we have heat one plus heat two over
The
uh
total heat capacity mass
well, yeah.
some multiplier thing, whatever you call that
that
value.
that thing plus the other one.
Yeah. That
All
thing
right.
plus the other thing.
So we'll just take this and we'll put it here and call it good and not try to
Okay.
redo that.
Yeah, you know what? That sounds good.
Somebody
So,
else did it for us a long time ago.
okay, so but the challenge is for us to yeah, let's delete all that and let's just start from where we were. Okay, perfect. Look at us
Cool.
being awesome.
Yeah,
Okay,
we're learning stuff. Learn every day.
a little smarter, a little smarter.
Yeah.
Okay,
So
so
this is the temperature that
right,
we would have to change to this.
which the temperature just so right now, just for like, absolute foolproof clarity, it simply just does not include those two terms, right?
Uh,
Is that what's going
this
on
is
here?
the heat,
Yeah. And this is
and this is the height. but there's no temperature. So this is a mixing of temperatures.
Oh, right. And this is just flow.
This is just calculate the temperature of a pixel.
Oh, this is just calculated temperature, so not even.
So yeah, well here, what is T1 here? Well, T1 is M1 C1 T1 over M1 C1. That's recursive. No, this is heat.
Got it.
So this is heat. That is height.
Hmm.
Well, without the C1 because there's no C1.
Right. Well, C1, C, so this is one, your favorite thing. That's one and that's one right now.
It's like H1,
Yeah.
and this
Well,
is just
and I
M1.
mean, the capacity terms are one, is what I'm saying.
Yes, it
I'm
could
using
be.
the word one a lot.
Yes.
Anyway. Okay. So if you want to calculate the temperature at a location in order to do this, so now we're going
Hmm.
to have to take into account multiple materials,
Exactly.
which according to this means that you actually need, wait, so hold on, this is multiple temperatures mixing together.
Hmm.
So, okay,
Which we can calculate up here.
right. So hold on, bear with me since we're just calculating the temperature of one pixel.
Uh-huh.
The temperature is equal to the temperature, which is equal to the temperature, right? Because you're in one pixel. So all of those terms should be exactly the same, right?
Uh, yes.
So
That's the
then
way.
if
That's the way we define it in this
right,
universe.
in this thing. So this term, which is the heat,
Hmm.
you already know, what am I getting at here? You already know that at least that the temperature is a part of that heat value.
Hmm.
So in order to get the actual temperature from the heat, you want to solve this equation for what's your input variable?
What do you mean?
Capacities. It's your capacities, your M2, M1C1, M2C2, right?
Well, capacities are known, but the amounts are also known. So you know these amounts and these capacities, and you know this because that's heat. Or actually, you know
Right.
this whole sum.
Well,
You know the whole sum of this,
you know the sum, you don't know the individual like amounts, is what I'm saying.
which you don't care about. It's just this pixel.r, which is the heat of this pixel.
Hmm.
And then here we just have to sum up the amount times the capacity of that pixel.
Oh, right, of course. Yeah. Okay, so you have this value and you just do that. Right.
Yeah.
And then when you go
But
the other direction, yeah, then you just,
mhm,
okay, that's fine. So then, yeah, then you just take your temperature and you multiply by the sum of the height times capacities. So it's not even the
yes,
average, it's
but
the sum of the height times capacities.
right. And so that's what we were doing last time wrong as well, because we were dividing by the
We were
to get
getting
the
the
average
average,
capacity.
which we
It's which
didn't
is
need. We need the total capacity.
yeah, we need the total capacity of the cell, which
Thanks,
makes
math.
sense. You got the heat, the total heat of the cell divided by the total capacity of the cell
Right.
gives you temperature.
All right, so this little foray down math lane has actually proven useful.
I suppose so, because we now did not once again use the wrong equation.
Yep. Okay,
Let's see if I can. Let's see if I can do this.
I'm
Copy
ready.
paste.
Hit me with it.
Fail
What do
me
we got?
now. Oh yes. All right. So those are the capacities that we had last time.
Wait, these are okay, but these are
These are the
average
wrong
capacities. These
capacities.
are the wrong
Yeah.
capacities.
So
Oh, this is literally just the
because
code that we
that,
had last time.
yeah, it's literally the code we had last time.
Okay.
So that just should not be divided by height.
Mm-hmm.
This should be not called average capacity, but rather total capacity.
Total vapacity.
Vapacity. Vapacity. Uh-huh. All right, so we have the total capacity. Um, problematic, added more elements. What do we have here? Water, steam, lava, dirt, copper, obsidian. Water, steam, lava, dirt, copper. We need obsidian for all of these. Oh boy.
Yay. Aren't
So
you going to
what?
be excited to come back and like edit all this code when you have 100 elements or something?
I need to do it a better way.
So,
I did it for the code inside, but not for the code outside.
well, you could this is a longer tangent, and I'm actually some one of the things I'm actually thinking about doing. Tell me if you'd be interested in this. Is I want to do a stream maybe like every other week or so on on coding patterns and stuff like interesting ways of solving common problems.
Mhm.
Um, so one of the ways that you could solve this is to write your shader as a shader generator, and
True.
you write it as a you write the code to write your code for you, and then you just punch in how many elements you want, and it just generates it all for you.
Sounds very CMake,
Yeah,
and I
pretty
like it.
much. Yeah,
I'm just eyeballing Obsidian right there. I don't
do
know
it.
what it is,
That's
but
you forgot to change the name.
oh, I did. That's true.
Let me just put a big old circle on your screen.
Thanks. I can't see it.
Oh,
Oh
you like to
no,
see, huh?
alignment issues.
Oh, but your equals are not aligned. Ah, that hurts
Oh God. And then I save it in auto formats and
me.
just leave it like that,
Yep.
just free.
I twitch. I twitch.
Yo, yo, yo. Okay, we're doing it. This
It-
is good.
oh my
This
God.
is
You know what?
satisfying coding right here. We're just gonna do that. All right. Scrolling past.
Moving on.
Um, so we have Obsidian and the total capacities for all of the directions because we
Yep.
need this north, east, south, and west. So to calculate the temperature, as we were saying, it is this pixel divided by the total capacity. So in fact, we don't even need this height. Height does not factor into the
Right.
equation at all.
Because well, right because the height is now included in the capacity.
Multiplied by some certain stuff. Yeah. We do it like this. Total capacity. I don't know. Yep, yep, yep. All right. So that's temperatures.
Yep.
None
I'm
of this needs to change
right because yeah.
because once you have the temperature, then you just calculate the flow. Dir.
Dirt temperature differences.
Mm-hmm. Let's see what it does.
I should do nothing. Wait.
It should break everything
No, that's true. Yeah, I should break
because
everything.
state changes are just gonna go crazy.
JK,
But
LOL.
it shouldn't change anything about like water in and of itself
Yeah.
or lava in and of itself. But
Okay.
when you put lava on water,
Problems.
woo!
Actually, I mean,
I mean, like it looks pretty good.
yeah, this seems to work okay. It's
Yeah, we got a giant heat cannon going
we
up. We got
do have a big old heat cannon. Hey, and it's
we
raining over
got
there.
rain. Yeah, so things aren't totally breaking.
Colin, switch back to the non-false color view. Is that it's forming obsidian down there? Is that the deal?
Yeah, it's a big block of so that's
So, well, this
obsidian.
is good though because right, because the water's cold heat or capacity for cold, basically, or lack or heat capacity. I don't know, whatever. You know what I'm talking about? Like
Yeah,
it over uh, flowed the amount of heat that the lava could provide.
yes. So all of the lava turns to obsidian while a lot of steam is generated,
Did it just
and in
work
the end,
first
everyone.
time? Is that what I just saw here?
I mean, like, yeah, but I'm worried about it.
I know. I hate when things work first time. It's like, oh, did I do that right? Am I just
So,
totally
I,
missing something?
I mean, I'm just gonna branch and commit it there. So,
That sounds good. Yeah.
what stream is this? Is it like stream three? What's this one called? I don't know what this one's called.
Uh, this is well, okay, yeah. I should probably start coming up with a name for this. You know what? This is actually something we should do on a pre-show is come up with a name because right now it's just
Hmm.
shaders for fun and profit.
I mean, I thought that was the name of the last one. It is a
It
pretty good name.
was.
So I'm just gonna create the branch called Brothers Code 3
What is your game called, by the way? Like, do you have a name for it yet?
Flow.
Flow. Okay, that's good. That's good.
Yeah, currently, because I don't know what it's about other than stuff's gonna flow, and then now
You
we're here.
know, ship it.
All right, we're staged. Temperature shader added the first inkling of capacities. Push that. Always commit and push. Never just commit.
Yep. Otherwise, when your
Who needs
computer
to?
dies, you have
Well, also
problems.
that, but who needs to rehash their commits into elegant change logs? Nobody. That's who.
Do you use branching, like feature branching?
Feature branching.
Yeah.
Like here or at work? Because like that's my branch so far.
Nice.
I have one that's called What when we didn't know what was happening. But now we're on Brothers Code 3,
Okay,
and that
that's
will
good.
be pull requested to myself
Ooh, there you
immediately. So,
go. Now you're getting fancy.
oh yeah. So we have some capacities.
Yeah,
Very
we
cool.
do. That's pretty neat.
Hmm.
So, okay, so now
What time are we at?
wait, we are at like 10:30. So you want to take a quick break and then see if we can get like amounts in there as well?
Yeah, sounds good to me.
All right. We will be right back, everybody. There's the button. Hello, we're back. It's time for more coding. And this time I'm
All right.
actually going to switch away to look not just at my pretty face, but also at your pretty code.
Super.
You're
Uh,
like, that's great. Thank you.
yeah, debatably pretty, my code. I mean, my equal signs don't align,
You know what? Yeah, we're going to have a discussion about this later, let me tell you.
but is that one thing that your generator can solve for me?
Yeah,
The shader
let's go
generator.
line that up right there.
Ah,
Just
I
saying.
kind of want to do it now.
No,
Why
no.
isn't
You
that a Clang format? Is that a
that
Clang format thing? Can you make it do that?
I don't know. I don't know.
Just
I
because
use an
it's
auto formatter too. This is actually something I'm going to talk about in
just
when
like
I do
space.
uh, the next whatever the heck I'm calling this thing now, Harmony, Omnibus, whatever my library is. When I do that stream, I'm gonna have an auto formatter that I just added to it, but I don't think it lines stuff up, sadly.
Uh, it should do this,
I know
like just for I
it
don't
would
know.
be awesome, right?
Yeah.
Can't
So
get
we
everything you
have
want. Anyway,
temperature,
back to real coding. Yeah.
yeah,
Man, we are
temperature with
productive.
capacity. We're working hard.
Yeah, we are. Okay, so we got capacity. Right. Okay, so now are we gonna try changing the amounts? Is that the next piece?
Well, so in the heat shader, so this water, steam, lava. Does anything else flow? No, nothing else flows. Um, pretty sure nothing else flows. What we got here? Water, steam, lava, dirt, copper, city. Yeah, all right. So in the heat shader, this pulls things with it when it flows.
Got it. Okay, right.
And based on your capacity, you'll need to flow a different amount of heat out.
Yeah.
So this is fine, but in the uh, element shader, where it actually calculates those values, here,
Mm-hmm.
we need to figure out how much as a percentage of the other element got taken to maintain the temperature. Make
Can you
sense?
just compute the result and then back calculate the amount? Like,
Hmm,
assuming that you want the temperature to stay the same,
yes.
then you just say, okay, well, this much stuff flowed, so clearly it must have been this amount in order to maintain the temperature.
Yes, and for some reason my control click and my F12 doesn't work, so we should scroll up here. So this is the get heat. So based on how much flowed, and what my heat is, and what my height is, height being the total sum of all of the elements in the
Right, total quantity.
total
Yep,
quantity, and their heat and their height.
yep.
This is the percentage of stuff that flowed,
Percentage
and
of
then
quantity, so that flowed, right?
of quantity that flowed.
Okay.
And right now, I just take that certain percent times my heat. So assuming it's flowing out, this
Mm-hmm.
is percent times my heat, and use that. But that doesn't work if you're flowing only water out of a cell and there's dirt staying in it.
Because you want to flow more heat than you would otherwise.
Yeah, because then if the water only takes if like the one
Right.
third of the cell is water and that one third flows out, it doesn't take one third of the heat. It takes like 90% of the heat. Otherwise, the temperature of the dirt would just skyrocket,
Right. So you need to have,
which we can actually test.
do you need two capacity or two flows then? Do you need a material flow and a heat capacity flow?
There is, yeah, cool. So that worked. As the water flows out of this dirt,
Hmm.
there's massive heat and it turns to steam. Even though dirt is placed at point 0.3 and water is placed at point 0.3, like the point 0.3 temperatures,
Hmm. Yeah, why does it
when
do
the
that then?
water flows out, it creates steam
Why?
because the dirt, it's assuming that the dirt has the same heat capacity, but it doesn't. It has a much lower heat capacity. So
Okay.
in this cell, you have like this much dirt and this water flows out
Hmm.
and so it takes half the heat and in you have this much heat in the cell, so this much heat goes away. But water has a heat capacity like here, and dirt has a heat capacity like here. So when you take
Oh,
that much heat and you jam it into that dirt, you
right.
can
Then
jam
it's
it
like,
in
hey, it's got a lot of
this many
temperature.
times. Yeah, and then it's like
Yeah,
five temperature, and the steam just boils off.
I see. And so yeah, whatever's left is just like, oh man, it's really hot in here, and then steams.
Yeah,
Okay, cool.
so verified. Does need a fix.
Okay, because water boils for no reason.
Yes, and water boiling for no reason is not a feature of this physical environment.
I mean, we get to make the physics, but
Mhm. I don't want it to be though. Doesn't make sense. My world.
I'm changing the name on here. Water two, or at least a little box down on the side. So things we're doing: water to larger quantity of steam and heat capacity redo.
Yes.
Oop, I don't know why I just clicked there. Don't mind me. Okay, so
So we have some
the ch
percentage flow that we know.
this is so percentage flow, however, is based on quantities, not on heat capacity. There's no knowledge of heat capacity in here at all, right?
Nope, because
Okay,
I took all the capacities out.
right. So this is a problem.
Yes. Um, the heat capacities are currently declared in the something temperature shader. Yeah, temperature
Hmm.
shader.
Oh, you can just copy
Which
pasta that, but
absolutely. Um, but do we need to know the total capacities? So how do we calculate temperature here? We divide this heat by the total capacity.
hmm.
All right. All right. Hmm.
Well, okay, so in your get heat function, does it just need to know, can you get the amount that says where you call get heat in the other shader?
Yes.
At the point where you
In the
call
element
it, does it know the all the elements that have flowed?
it knows itself, and all of the elements are flowing at the same time. So they should all be calculating the same values. But you don't want to calculate all the elements, all the values in every shader.
So, okay, can you go to where get heat gets called in here?
Yeah. So that's at the end. So this is
Yeah.
after the flow for this element. So you know this pixel, the total
Oh,
height
this is a
and heat,
single element. Okay.
is a single element.
Yeah.
And then it tells how much of this element flowed with regards to the next pixel's height, which is the total of all elements.
Hmm.
Because it assumes that if you have one cell, so this cell has a bunch of different elements in it that can flow, that all
Right.
of those elements will flow equally into the next cell.
Because it's based on the total height there, not the height of just your element.
Yes.
Got
Granted,
it.
that's not how it works.
No?
Uh, no, because you have a flow divisor.
Right.
Some,
Okay. Yeah, to give it the gradient, which is fine.
yeah. Well, no, that's a flow gradient. The flow divisor is how things act, how fast things actually flow.
Oh, right, right, right. Okay.
Um, but yeah, so this assumes like if you have half lava and half water, the water will say, oh well, I'm flowing half of myself, and the other one's flowing half of itself. But it's always going to be lower, so it never goes up,
Hmm.
but it will go down. So lava only flows a quarter of itself.
Okay. So like lava flows more slowly than water, and
Yes,
that's how you got steam to flow really fast, for instance.
yes, because steam flows just at maximum speed.
Okay. Cool.
Yeah.
So got it. So, but we
So
can still do, so based on the equation that we had for temperature, can we do each of these heat movements independently and still end up with a result that is temperature invariant?
in theory, because we already do it right now here.
Right, with everything being one capacity. So basically we just
Yes.
have to add a capacity into this element shader and then pass the capacity in as a parameter because this is a per element.
No,
No?
I think we could be more clever than.
Okay, all right, hit me with it. I'm ready for more clever.
So in the temperature shader, we
Yeah,
calculate all the temperatures
right.
and we calculate all the total capacities.
Yes.
for each pixel. Now this is because everything runs from the single shader list, which
Hmm.
doubles as the texture list. We know that the heat is finally calculated here, right?
Right.
So after this, so heat movement is the heat shader and heat flow is temperature shader. I should probably rename those, but that's a topic for another time.
Yeah, that's very clear.
Yes.
Okay, got
So
it.
the temperature shader is the last thing to run.
Hmm.
And then all of these run, all the elements then run.
Right.
And it's assumed that all the elements run at the same time. They have no dependencies.
Hmm.
Um, so what we could do is in the temperature shader, we take this capacity, because the capacity isn't going to change, and we can just store it in green. And the capacity this, total capacity this. Yep.
So is this to be used on the next frame?
Yes.
Okay.
So we store the conductivity, or sorry, the capacity of this pixel,
Yeah.
and then in the element shader here, we can just grab that from the heat pixel,
Hmm.
heat pixel.g.
Is the total capacity.
I don't know what we're using it for yet, but now we have the total capacity.
Neat.
Yes. Uh,
So
this is percentage heat flow. So this doesn't have to be touched. This is the percentage
I see where
um,
you're going. I see where you're going with this.
heights. Yeah.
So because the temperature is the sum, right, of the heats over the or over the total capacity,
Double checking. Temperature is
or is
heats over capacity. Yeah.
remember that equation that we
Yeah.
had? It was like, yeah, it was capacity times temperature plus capacity times temperature over total
Which
capacity
are
times
heats.
temperatures,
Yeah.
which are heats. Yeah. Okay. So yeah, so that's where you're going with this, right? That
Yeah.
now that you have the total capacity, in here you're going to have the individual heat.
Hmm.
Okay. All right. Let's have the next part.
All right. I don't know where I need this yet, so let's look at get heat.
All right.
I know it's something to do with this.
I'm gonna need to stick this
So
variable in there.
I mean,
We're gonna just
yeah, we could just straight up pass it in, but like I don't know what I need yet. So let's see. So when we get the heat, what do we want? We want to know what percentage of, or how much heat flowed
hmm
with whatever element that just flowed,
right.
which means we need to know the percentage of heat that this element had, and also the percentage of this element that flowed.
Okay. Hold on. There's yes. Yeah, that's right.
Yeah,
Yep.
so in a cell, half of it's water, but we know the heat here, that's an equal sign, paint skills,
Got it.
is 1, and the heat here is 0.1 because that's dirt or whatever.
Hmm.
And so when half of, or a third of this flows, we have to know that this had whatever, like 90% of the heat,
And you want to
and
get the
then a third
percentage.
of 90% of the total needs to go.
A third of 90% of the okay. Yeah. Yeah.
Because a third of it flowed,
Right.
and the water had 90% of the heat.
Okay. So I think I know. I think I know how to get to this. So
All right.
we so remember T equals was it H1 plus H or hold on T1 wasn't it this T2
Hmm.
over H1 plus H2
I mean, that's
where
a resistor equation.
it's heat capacities. So this is well, isn't this is what the temperature like mixing temperatures of two fluids was, right?
Uh, that's what it was.
Right. Okay. So Now that you have what you have is the total, right? So you have
Uh,
M1C1 plus M2C2.
M1C1 plus M2C2.
Isn't that your total?
Yes.
Okay.
That's total capacities.
Okay, cool. And then you have H1 and H2 because those are just like H1 is M1C1 T1, right?
Yes.
Plus yeah, okay. Yeah, this is right.
Mm-hmm. H1
So,
is M1C1 T1, H2 C2 C2.
okay. So you and then you also know in here you know this amount, right? Because you have your own capacity in this element. My mouse is all up in the
Yes.
way. Move my mouse over
You
there.
you know your capacity and you know well, you don't
You
know
know,
which element you are.
you yeah, you do. You know which element you are.
No, you don't. There's a
What?
generator.
Okay,
A
but
capacitant is a
you
parameter.
could pass it in. You could pass it in. So you
Yeah.
would know this, but and you
Yeah.
know that this value is equal to the total. It's hold on, tot cap
Uh-huh. Times
times
the temperature.
temperature uh minus wait yeah this value oh,
All the
no you know this
rest of the
value
elements.
so right so actually all the rest of the elements is the total capacity times temperature minus this thing that you know, right?
Wait,
So
what?
you can get this term. You can get the sum of all of
Ah,
these
yeah,
terms
yeah.
for all
You,
the
you
other
can get
elements,
you can get
right?
all that.
So which
Yeah.
means that you can use this information to do the equation twice, once for what it was, and then once for what it's going to be, and then that's how you flow stuff.
Yes. So from the heat pixel data, we know our, do we know our temperature? We don't know our temperature.
Oh, we don't know our temperature?
So we're going to know our temperature.
All
Yeah,
right,
no, we
yeah,
do.
let's.
Temperature's an alpha.
Oh, temperature's alpha. Okay, good.
Wait, but is this true?
Uh-oh.
Uh-oh.
Uh-oh. We have a small problem. Hmm.
uh, it's
It's just total capacity.
that.
Yeah.
Okay, hope that didn't
Away we
break anything.
go. Yep, let's run it. Let's see what happens.
All right.
Oh wait, yeah, you got to store that in
Just
a variable. I was just gonna
let's just
complain. Already
not.
that.
Um,
Hmm.
yep.
Good thing you're in a branch, eh?
Yeah. Right. Well, everything is white. Or undeclared. Oh, we're writing stuff in a shader. Uh,
Hmm.
just do this equation, okay, shader?
Hey, yeah. Hey, could you just run this for me? Like solve it?
Yeah.
Thanks.
All right. So we have water.
Hmm.
Okay. Promising.
Water's
Okay. We'll put some lava on it. Is there steam? Yeah, there's steam.
there's still
I know
steam.
steam. The heat is intense.
Yeah.
The intensity of the sun, but it seems to not be breaking anything, which is cool.
Yeah.
We got
Yeah,
our obsidian
yeah,
forming.
you're forming obsidian. You're kind of growing obsidian there. That's cool.
Yeah. This.
Where's
Oh
all that
God,
heat going?
that's so hot. It's 1.6.
This
Like
is
it got hotter
it's so hot right now.
than the lava. It's so hot right now. Like lava spawns. Oh Jesus.
2.4?
No. No.
Because
No. No. No.
Because yes, it does. Wait, no. Okay, you know why? Because you're setting the temperature and you're not paying attention to what its heat capacity is.
Yup. That's why.
Yeah.
So when in my place element function, I'm just like, YOLO, this is gonna be the temperature.
And you're like, uh-huh.
Uh, and then somewhere
And
over
and then where you
here,
use the
if
temperature,
I want to change the heat, here's the temperature. The new heat value is the temperature times the delta amount. So temperature needs to be temperature times capacity, right? Wait,
new heat value is temperature
I
over
want to
capacity.
add heat. Temperature divided by capacity divided by temperature divided by capacity. In this, I will have to declare in all of these sections
Lovely.
the same as, oh God, man, you know what I really use? Like a generator.
Yeah, if you really want to just take like a lot of time away from, building the game part, then you could write some cool tools.
Yes. And then I don't know what I would do with that.
Yeah, exactly.
Dirt. Where's dirt? Dirt is this one. Up, up. Oh, good content right here. About my cap scaling. So I need cap scaling.
Is that just
Keeping all
water?
these in line is going to be fun.
It's just fine. I don't know what you're talking about.
Yeah. Yeah.
It's
Well,
complaining that
I'm going
it's.
to need a float capacity.
Oh yeah, that too. It's also complaining that those are doubles, not floats.
Oh, really? Is it going to
Yeah,
do that? Going to do me like that?
it's an every single one.
Uh, Unity. Unity.
Types. Yeah.
So let's just take that some of this, um, and then distribute those kind of like that. Obsidian is this. Water is here. So we have to do this because otherwise it spawns at a temperature that we don't know about.
Hmm.
Just have water? No, that's water steam. But what is heat going to do? Oh, heat doesn't add heat, so that's fine. All good.
Wait, heat doesn't add heat? What does that mean?
When you place heat, it doesn't try to add heat to the heat layer when you're doing it. It
Okay.
just straight up adds heat and doesn't.
Oh, I see. It doesn't care about what temperature it is.
Well, yeah. Well, because like if you add a physical element,
Hmm.
then you have to change the heat in the cell based upon what you added. But if you're adding heat, like it doesn't care.
Got. Oh, right. Yeah, of course. Got it. That's like a secondary.
So what happens now? We place some lava, and it's 6.4.
That's a little higher than you want it to be.
That's a lot higher than I wanted it to be.
Hmm.
Why is it
It appears to have gone the other direction.
capacities? So capacity is less than one.
Hmm. Well, temperature over capacity is greater than one.
New heat value. So I have a temperature. I have a heat and a capacity. I need to multiply it.
Yeah, capacity times temperature. I was wrong. That was my bad.
Well,
Right. Yep. Temperature times capacity. Rip.
gives you heat. So we have water.
Okay.
Hey, it's 0.3. We have lava. Hey, it's 0.9. All right, so everything's the right temperature now. We got some steam. We got heat.
Still looks really cool.
Still looks really cool. At least it's not over the. It's got conservation of heat. I think.
Yeah, looks right.
I don't know.
Cursory
Yeah,
inspection says nailed it.
it's not. It's not 6. So
Yeah.
victory.
Okay, so back to
And
back to
I
regularly
forgot what we
scheduled
were
programming.
doing.
You were going to pass the yeah, the
Yeah,
temperature.
we're doing something here.
Right. So, okay, because we want the percent flow not just of material, we want the percent flow of heat.
Right, because we were doing this with the dirt, and
Hmm.
then we're flowing water out of the dirt, and it
And
turns
it's like,
instantly
oh,
into
hey, look,
lava and
it's
steam.
the water turned into lava.
No, the dirt turns into lava
That's amazing.
because it gets so hot.
Yeah, okay, I should probably fix that. Hey guys, let me show you a magic trick.
You add a little bit
Just
of water to some
dump,
dirt.
yeah, just dump a glass of water on the floor, like this, just tunnel starts going down. It's like, why did you do that? Physics. I found a bug in their
uh,
shader.
uh,
All
this is
right.
how religions are founded.
Yeah, the little lemmings in your world are going to be dumping glasses of water on the ground and just freaking out.
Exactly. So how do we fix that? Something
Uh,
about get heat. We have to calculate some stuff here.
right.
So we need
So
the total cap times the temperature, which, right, that's why we
that's why you
figured
need the
that out, is
temperature.
because this is true now.
Yes. Right. Yeah, we just changed the total capacity.
So we need some, let's say, float my temperature, float my, what is
Boat.
it? Yeah, my total capacity. So we need those. And that's this. My total capacity is here.
Yep.
My temperature is here.
Yep. So
So
far so good.
assuming outflow, um, this we can come back to. No,
Hmm.
we can't. That's the only equation left. So this is the
So
plus
that's the everybody
the
else.
rest.
Yeah.
Hmm. And we
So
want to know what again? Oh,
s-
my percentage of the total heat.
of the total heat. Yeah.
So this is, well, no, well, this is my heat,
Hmm.
and this is the total heat.
So, but you're okay. So, right. So, but you're gonna be flowing a percentage of your heat. So
Hmm.
you what you do is you calculate whatever percentage of this value actually gets flowed, and
Hmm.
then so first you calculate the rest, right, by subtracting this thing, this value from this, right?
Wait, hold on.
So first you calculate this
How do we calculate that?
because you subtract, so you know this value, and you know,
Which is the temperature in this cell.
right. So you
So
make this a minus that
okay,
equals the
there's too
rest.
much. There's too much stuff.
Okay. So because first you calculate the rest, right?
Yeah, just put it on the other side. So
Okay.
my amount of this element,
Hmm.
I know.
Times my
I'm just gonna get rid of these. Get rid of these a little bit.
okay.
Uh, by my here, it means this pixel
Hmm.
in total.
Uh,
Uh,
well, my total capacity is my total,
is of this cell, and the temperature is the temperature of this cell.
right, of the cell. Yeah. But in
Yeah,
this case, you
and
want just the capacity of
the
you.
element capacity, and the element amount.
Hmm. Yep.
Okay, cool. So that could be element capacity, and that could be element amount
Yep.
equals the rest.
Right.
Float the rest.
Well, okay. So yes, you probably separate out this as a variable as well, because that's the amount that you're just gonna need to flow,
Um,
or you're gonna need to flow from that amount. However you say that. Does that does that sound right?
so this is the no, this is the total amount of heat belonging to the element that is flowing.
Right. And so you're gonna need to flow a percentage of that based on your flow value.
But do we then care about the rest?
Yes, because you have to, in order to calculate a percentage, you need to be able to
Well,
do it
I
backward,
only
right?
needed to calculate percentage so I could calculate the heat of this element.
You don't need to know how much heat is present afterward in your
Hey, just subtract whatever you took out.
right, but to
Yeah.
calculate to get the temperature to stay
Let's
constant.
let's just go on and see what
All right,
happens.
sure.
So
Yeah, maybe you don't need the
so
rest,
we
but I
have the
think
heat
you
of this
do.
element and we have the rest.
Yeah.
So the amount of this that flowed, but I need to know the amount of this element that
Hmm.
flowed. So the element amount, the flow divided by the element amount, float percentage of flow out equals that much. Actually, max. Max with small, so we don't get divided by zero errors.
Yeah.
Hooray. And then that times the heat of this element times percentage flow out
Hmm.
equals, we look at percentage to flow and percentage flow out. It's good.
It's great variable
Uh,
naming.
so I'm doing this backwards. Heat of this element times percentage flow out is heat out equals heat out and heat amount out. It's great. Is that much?
Yep.
Ta-da! So we don't need the rest.
So heat of this element is
Because all I'm looking for is the amount out.
element is percentage of flow out. Okay, but hold on. This gives you, wait, this gives you, right, but this gives you heat out. This doesn't give you percentage of heat out.
We don't need percentage. We just need the physical number of heats.
Oh, okay, in that case, you're good.
Hooray! All right, so this goes down. This gets renamed to percent flow out. This gets renamed to heat amount out.
Then I have to do the same thing the other direction.
And then we copy paste this structure as in and stick a negative around it. Something like that. Oop. To
So
select
you're
the one
fixing the
that isn't.
directionality of these?
Yeah, it's because flow could be negative,
Hmm.
and that just means it's in.
Right.
Uh,
Wait, if
yeah,
flow is
wait.
negative, then it's,
No,
yeah,
no, it's in. It's inflow. Inflow is positive.
yeah,
Inflow is
inflow is
always
positive.
positive. Yeah,
So the part you said assuming outflow,
yeah, that's assuming inflow.
okay.
Well, uh,
Directions.
yeah. Oh god, we had a whole go back to whatever stream two. Brothers coding. You can find
Yep.
all about direction.
We just had the worst time with that. Oh my
Yeah.
God. Hey, but it
Uh,
eventually got itself sorted out, right?
yeah, it did. It did. So this is not working though.
Why not?
So so outflow works. So outflow is then heat as element times percent flow. And because flow is negative,
Hmm.
right, this is selected. And the heat of this element is true. Like that's just
Yep.
straight up true. So, but the percent flow in relies here on
Uh-oh. It's their everything.
their element. So heat
Yeah.
of that element or their element
Sure.
is the element is their element amount, which I guess then this could be my element amount. Oh, you like that mix of styles right
It's
there?
it's nice. Yeah,
Oh yeah,
that's some that's some
got a little
nice
bit of C sharp,
styling.
the C plus plus.
Heck yeah.
Oh, why did
Look
I do this
at
to myself? Oh, it's even the same
that. It's
here.
everywhere. I
Ah,
don't...
all right. There'll be a cleanup
Perfect.
podcast sometime or
Yep.
whatever to stream. My element amount. So I need to know their element amount
Yep.
times it's the same element capacity, and it's their temperature. So that works.
Yeah. So you didn't use my total capacity, right?
Did I?
I don't think
I
so,
didn't.
which seems weird, but
My amount times element capacity times my temperature. Well, because I already know my temperature, so I don't need my total capacity.
okay.
Nope. I need to know that.
Hmm.
And so the percent flow in, copy from here a little bit, but is on their element amount. And the heat amount in would then be the heat of their element times the percent flow in, which is 0. One of these is 0.
Hmm.
Um, should be 0. I don't know. In any case,
That seems
we
right.
do that. And so calculate flow.
And then we confidently delete lines 94 through 101, right?
Yes.
Like
One of
that's
these will be negative, or both 0 equal heights. If equal. Nope, that's just calculating stuff. Up. Or both 0 equal.
Yep.
And then this is how we figure out how much will actually flow. And then we be clever.
Cool.
Neat. So this,
Now we
what
just
is this
gotta
doing here?
pass the rest of the
Calculate
parameters.
the heat of the actual element that is flowing. Yep, we have my temperature, my element. We need their temperature and their element amount. And the element capacity. fix everything down here. So when we get heat, we need the flow.
Got
We
it.
need my temperature, which
So
is
far, so
heat
good.
pixel A. We need my element amount, which is this pixel R. Hup. We need their temperature, which is heat pixel north
Mm-hmm.
dot A.
A.
Yeah, yeah. Yes, this is
Okay.
just the northern.
Yeah.
That's
Yeah. Yeah.
their temperature. Their amount is this pixel's north dot R. And the element, so why did, oh, right, because we didn't need total capacity,
Mm-hmm.
correct?
But then you do need element capacity.
So we don't need that. We also don't need the conductivity. We still have B and A free, or B and G free.
Cool.
Yeah, but we do need um,
This is gonna be a new parameter, right?
element capacity. Exactly.
Cool.
So that's the same here, except for east. Whoop, up. Yellow. Did that work? Oh, yeah. All right, cool. Well, that probably took longer than.
Yeah, but it looks fancy though, so that's the important part.
I gotta confuse the viewers, right?
Yep. Like, what just happened?
Yeah, so
Oh,
that's the same thing, but with an E instead of an N.
yeah. Cool.
Because we only need to keep track of the inward east and inward north, nice capital
Mhm.
letters. We know it's
Yep, because style is consistent.
a. Amen. So much
Yeah,
style.
just saying.
So where do I need to do that? So new thing
Yeah.
means a new thing up here. Flip that. And it means a new thing up here. Just copy it again. Laziness wins every time.
Fancy.
And then this has to be, ooh, are you ready for this?
Hmm.
My main script is actually somewhat nice because this is where you initialize all the textures, and this is where you initialize all the materials, and this is all the common material stuff. So
Hey,
here we just say, hey, whoever has, no, we can't do it here.
why not?
Element capacity, because they're all different.
Well, you could call a function here based on what the material is,
Wait, what? Yeah, I
right?
could.
So, yeah, just
I
call a
could make
function. And
I could
because
make a
then,
switch statement.
well, no, you could call a function, and then in that function, you could call the same function later when you're actually placing. Remember where we had to adjust it for changing when you're adding material, changing the temperature?
Right.
So you call that same function from there, and then you can have all this stuff in one place.
Yeah. Private, what is this? A float get
Yep.
capacity.
Yeah.
And this takes a, what does it take? Material.
Material.
Mat.
Yeah.
Cool. And then we just switch mat
Hmm. You can
based
just
on
go,
this.
yeah, grab all that
Oh, no, it's an element selection.
element selection.
Yeah, no, that'll be fine. That
Okay.
one's an element selection. This one's a material. So we actually should switch on material.
Hmm.
Uh, but yeah, I'm just gonna have to do some stuff at the bottom. So we have to switch here a little bit this way. Up, up, up.
Why is element selection different from material? Just for my
Because
knowledge.
element selection is the things you can press in numbers keys to select.
Oh, I see. And is there no map between element selection and material?
No, there probably should be.
You can make another function.
Can make another function. Yes, I could. Or I could just do that. Hep, hop, bonk, 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 bonk. Did it.
You took the easy way out.
Right. So this is switches based on the material. Return 0, I guess, so it doesn't cry at me too hard. Cap scaling. Cap scaling.
Magic numbers. Magic numbers everywhere.
Just absolute. Block, 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 block. And then, of course, I don't need break statements. I need break statements, so I have return statements. Oh, I could inline all of this and make it look pretty.
Yay.
That's just grunt work though. So
Yeah.
here I'll actually then need to say where I get them from. Uh, Something like that. Oh no. Oh no.
So good.
Just the worst. Uh, I'm sorry. Sorry,
You got
viewers.
comments in your comments.
I got comments everywhere. Uh, and then these could be in there, and whatever. I'll fix it later.
Yep.
The mantra of a true programmer.
Yeah, fix it later, exactly.
So do I need to fix these now? I don't think
Nope.
so.
Nope. Really, you're just
God.
leaving that duplicate code. It's hurts your soul a little bit, but you know what? It's fine.
Yeah. Oh man. Uh, but this, I'm not sure. I'm not sure this is nice. This is gonna play nice.
Well,
So,
hmm,
oh no, okay. So the element capacity will return 0 and try to set that value to the materials that don't have that value, so it doesn't matter.
yeah, which you don't run the shader for anyway, right?
I shouldn't. I hope so.
Okay.
We'll find out. Are we ready?
Kinda not really.
I mean, what could possibly go wrong?
Yeah, exactly.
Water. Ah, still water. Lava. There's steam.
There's steam.
Heat looks.
Okay, hold on. Oh, wait,
Oh,
oh no.
heat's good.
I thought
Heat's
I started
good.
doing that. All right, heat's temperature's okay.
Yeah.
Really?
Temperature stable. That's it's cooling off here. I mean, I
Is it
guess it.
doing anything?
Well, I mean, so we'll go back to the litmus test we had before. If I put down dirt
Yeah.
and then put water in the dirt, does it turn to lava and steam? Huh. The answer's no. We did it. We did a thing. It's the right temperature. Everything's the
Hold
right
on,
temperature.
hold on, hold on. There's 1 second here. Did you just tell me that live on stream we made a new feature, fixed some bugs with it, and it's working?
I'm pretty sure you could put a check mark beside that. Stream
Woo!
first.
All right, big old check mark. This one gets like
uh,
Oh my God, really?
Splendid. Yeah.
That's
Yeah.
awesome. Holy cow. Can you clear my check marks? I really don't want to erase them by hand.
Yes, of
Thanks,
course.
buddy.
There you go. I'll give you a copper. I'll give you a copper check mark instead. Oh shit.
That
Oh no.
was too
Oh
perfect. It's just on
no.
fire.
We failed again.
Oh my God. Oh my God. Okay, well,
Next time on Brothers
next.
Code, figure out
Eh,
why this happened.
Okay,
Uh,
yeah, this looks like a job for next time. Just had to go and open our big mouths, right?
yeah.
Whoops. Well, this has been fun.
Yeah, it has.
Next time
Hands
we
it down.
decide we figure out why the universe is ending right now.
You're little leprechauns. You put too much water on the floor.
Okay, that was just I don't know any more perfect way to end the stream. So yeah, see y'all next time.